Today we will talk about ways to calculate limits and develop some techniques for doing so. First, let's look at a couple of obvious limits. The limit as x goes to a of x is a, which says if x goes to a, x goes to a. And if c is a constant, the limit as x goes to a of c is c. The constant is unaffected by the value of x. Now some formal laws. Assuming the limit as x goes to a of f of x is m, and the limit as x goes to a of g of x is n, where m and n are real numbers, then the limit of the sum is the sum of the limits, and the limit of the difference is the difference of the limits. If you multiply the function by a constant, the effect when you take the limit is that the limit gets multiplied by that same constant. You take the limit of the product. It's the product of the limits. And if you take the limit of a quotient, it's the quotient of the limits as long as the bottom limit is not 0. And if n is a positive integer, you take a function and raise it to a power. What happens to the limit is raised to that same power. Here's an example. Let's look at the limit as x goes to 2 of x squared plus 3x minus 4. Now you'll notice this is the sum and difference of terms. So we're going to have the lim as x goes to 2 of x squared plus the lim as x goes to 2 of 3x minus the lim as x goes to 2 of 4. Now x squared is a power, so we've just got the limit as x goes to 2 squared. 3x, the constant factors right out. We got 3 as the limit as x goes to 2 of x. And then the limit as x goes to 2 of 4 is just 4. Okay, and now the limit as x goes to 2 of x is 2. Same thing here. We get 2 squared plus 3 times 2 minus 4, or 6. Now, one of the things to notice here is this thing, 2 squared plus 3 times 2 minus 4, is exactly what you would get over here if you plugged in the function value 2 instead of taking the limit. And that's an important thing to know about polynomials. If p of x is a polynomial, then taking the limit is exactly the same as plugging in. Okay, not true of all functions, but for polynomials, the limit as x goes to a of p of x is p of a. And then the last thing we want to talk about in terms of a limit law is nth roots. The limit as x goes to a of the nth root of f of x is the nth root of the limit, and with the caveat here that if n is even, m has to be bigger than 0. We cannot be taking square roots of negative numbers. Now, as an example, let's take a look at the limit as x goes to 2 of 3x squared plus 4 over x cubed minus 5. That's a quotient, so the limit of the quotient is going to be the quotient of the limits. And what we see on the top is we got a polynomial. What we see on the bottom is we got a polynomial. We know that taking the limit is the same as plugging in. So that's just going to be 3 times 2 squared plus 4 on the top, 2 cubed minus 5 on the bottom. 16/3 is our limit. Now let's look at a limit that we've seen previously, the limit as x goes to 1 of x squared minus 1 over x minus 1. And if we look at the top, at 1, it's 0. At the bottom, it's 0. This is 0 over 0. The quotes mean that's not actually the limit. That is how we're thinking about the limit. And what we're seeing here is something where we don't know the answer. Such a limit, 0 over 0, is called an indeterminate form. Now this particular limit we've seen before. This is the thing that gives the slope of the tangent of y equals x squared at x equals 1. And this is similar to other limits that give slopes of tangents. They are almost always indeterminate forms, and we're going to have to do further work to figure out what the actual limit is. Here, the thing to do is to realize that the top factors. We do that, and now what we're going to do is we're going to write this not as a quotient, but we're going to write it as a product. And the product is the limit of x minus 1 over x minus 1 times the x plus 1. Now, if you look at this thing, x minus 1 over x minus 1 is 1 as long as x is not 1. But x is not allowed to be 1 during the limit process. So this thing is 1 throughout the entire limit process, which means that the limit is just the limit of 1, which is 1. And when we finish this process, this limit now is 1. This limit is a polynomial you plug in. You're going to get 2. So the answer is 1 times 2, or 2. Here we have a polynomial divided by a polynomial. When you put in 2 here, you get 4 minus 6 plus 2, or 0. When you put in 2 here, you get 4 minus 4, or 0. This is a 0 over 0 form. Once again, we're going to factor. Okay, so the top factors as x minus 2 times x minus 1, and the bottom, and x factors out as x times x minus 2. Notice the common x minus 2. We group those two together. That limit is going to give us 1. And then we've got this limit to worry about, but it's easy because it's just the limit of the top over the limit of the bottom. So we get 1 from here. And this is 2 minus 1, or 1 over 2. Limit is 1/2. Here's another indeterminate form. The limit as x goes to 4 of 1 minus x minus 1/4 over x minus 4. You plug in x equals 4. You get 1/4 minus 1/4, or 0 in the top. 4 minus 4, or 0 in the bottom. This is again this 0 over 0 indeterminate form. Here what we're going to do, however, is we're going to get a common denominator so that we can simplify the top. Okay, so 1 over x minus 1 over 4, the common denominator is 4x. So what we get here is 4 over 4x minus x over 4x divided by x minus 4. When we subtract those two, in the top we get 4 minus x. We've got a 4x, and then in the bottom, x minus 4. Now remember, dividing by x minus 4 is the same as multiplying by 1 over x minus 4, which you'll see right here. Here's the thing that was in the top. And notice that this term and this term are the same except for a minus sign. So this is really minus x minus 4. When we rewrite this then, that minus is over here. 4 minus x has become that minus x minus 4 over this x minus 4. That's going to give us our 1. And here's the 4x that's left over. And when you calculate this limit, that's a 1. This is minus 1 over 4 times 4. So when we're done, we got 1/16. Finally, let's look at the lim as x goes to 0 of absolute x over x. And of course, when you put in x equals 0, the absolute value of 0 is 0. So we've got another 0 over 0 indeterminate form. The point here is that absolute x is x when x is bigger than 0. And when x is less than 0, absolute x is positive, and we get that by multiplying by minus 1. So for instance, when x is minus 2, minus x is 2, which is the absolute value of minus 2. And what we're going to do then is we're going to break this into two one-sided limits. the limit as x goes to 0 plus of absolute x over x. Well, the absolute value of x is x when x is bigger than 0, which it is here. So we get the limit as x goes to 0 plus of x over x, which is 1. Now, we look at when x goes to 0 minus, now x is less than 0. Absolute x, when x is less than 0, is minus x. So this thing becomes minus x over x, and that's clearly minus 1. And as we've seen before, if the two one-sided limits are not equal, the two-sided limit does not exist. And in fact, it's important to note that the opposite is true. The two-sided limit exists if and only if both one-sided limits exist and are equal. Last, we consider the squeeze theorem. The squeeze theorem tells us that if you have a function h of x, which is trapped between two functions, f of x and g of x, and those two functions go the same place, and in this particular picture, they're going the same place when x equals 2, it says that h of x will go exactly the same place as the other two functions went. Here's a more precise statement of the squeeze theorem. Suppose that f of x is bigger than or equal to h of x is bigger than or equal to g of x, except possibly at x equals a, and the limit of f of x as x goes to a equals the limit as x goes to a of g of x equals L. Then the limit of h of x as x goes to a, the trapped function, is also L. This is also true about one-sided limits. If f of x and g of x trap h, and the limit as x goes to a plus of f of x is the same as the limit as x goes to a plus of g of x, then h of x, the trap function, is going there as well. So let's look at this particular example. What I want to do is look at the function sine of 1 over x and the related function x sine 1 over x. Now, all you really need to know about the sine function is that it oscillates between plus 1 and minus 1. As x gets close to 0, sine 1 over x oscillates wildly, and so wildly that when you come into 0, there's no limit. And that's true no matter whether you come in from the positive side or the negative side, so the two one-sided limits don't exist either. Now we're going to look at x sine 1 over x. Now, as we remarked, the sine function is always between plus 1 and minus 1. If x is bigger than 0, you can multiply everything here by it and not change the sense of the inequality, and you get minus x less than or equal to x sine 1 over x less than or equal to x. Okay. When x is bigger than 0, this thing is now trapped between the lower thing minus x and the upper thing plus x. As x goes to 0 plus, both of these things go to 0. So the squeeze theorem says that the trapped object, x sine 1 over x, goes to 0 as well. Now, if we looked at x goes to 0 minus, we would be able to do a similar thing. This limit is 0, and the result is the two-sided limit, x sine 1 over x, is 0. Now, if you want to see what's actually happening here, here's a graph of x sine 1 over x. You can see that it's infinitely oscillatory as you approach 0, but because of this x term, these values are headed towards 0. And if you look at the picture, here's y equals x. Here's y equals minus x. They trap these two. They go to 0. That's the plus limit. On the negative side, they trap it too. Now, however, minus x is the top. X is the bottom. X sine 1 over x is trapped, which means if you come in from either direction, the limit's going to be 0.